All right, good morning and welcome to the April Alta 2025 webinar series. Today we're going to be talking about optimizing carbon and nitrogen analysis in agriculture with Jessica Mannix from an application chemist from Elementar Americas. And just some logistics, we will have a Q&A at the end of the presentation today. That Q&A, if you can put questions in the chat, that's going to be the best way to get your questions asked. And feel free to drop those questions at any time. I'm going to ask people to try to remain with their videos off and muted during the presentation. If you have a complicated question, which sometimes comes up, we're going to invite you to come off mute and turn on your video if you'd like and ask that question and have some discussion with our presenter. But with that, Jessica, I'll hand it over to you. If you want to share screen, I'll stop sharing. Maybe I'll stop sharing.
Thank you, Corey.
Yeah, there you go. You should be able to share screen now.
Great. Let's get into my presentation mode here. Alrighty. Well, good morning and happy Earth Day, everyone. I'm really glad to be here with you all today. As Corey indicated, my name is Jessica Mannix and I am the application chemist here at Elementar Americas. Before we dive in, I'd like to take a brief moment just to introduce myself and the organization. So my background in biochemistry and soil sampling was obtained from SUNY ESF, the longest, I believe, university name in the United States, the College of Environmental Science and Forestry. But more explicitly, over the past few years with Elementar, I've had the chance to work hands-on with soil samples, providing data which supports nutrient cycles, contamination identification, the role soils play in supporting resilient ecosystems. Elementar itself is a global leader in analytical instrumentation. We measure carbon, nitrogen, sulfur, hydrogen, oxygen, and chlorine in organic and inorganic materials. And we'll touch on more about what that means in the coming slides. Our analyzers were based on the first generation, introduced over 125 years ago by Heraeus in Hanau, Germany, where they're still manufactured today. So I was lucky enough to head over there not once, but twice in the past few years I've been with Elementar as application chemist, which is a great opportunity. Right now, I'm presenting from our Elementar Americas office, which was founded in 1999. We moved from New Jersey to New York State, lucky for me. We're currently based in Long Island, New York. We serve the United States and Canada. We're also supported by a global network of over 80 countries. So if you have any friends or colleagues around the globe who'd like to reach out and connect with us, that's absolutely possible. And we'll share some of that contact information over at the end. I'm really looking forward to speaking with you all about combustion analysis, especially in the agricultural space, and hearing your thoughts as well. So thank you for being here, and let's get started. As a basic overview, we'll go and do an introduction into combustion analysis, speaking with Corey and the organization as a whole of Alta. We decided to be best to kind of start more on the broad end for those of you who are not super familiar with elemental analysis, maybe have never used an elemental analyzer before. So we'll go into the general parts of an analyzer. We'll go over some sample preparation and touch on maintenance as well. And then kind of the more interesting side of things for the organization, the agricultural applications, we'll take a look at some data and examples from soil, plant tissue, biomass, biochar, and even some fertilizer samples. All right, so what is elemental analysis? We're looking at the combustion or pyrolysis, typically of solids, but it could also be liquids to analyze the elemental composition. Combustion itself is the high temperature environment with the presence of oxygen. And what we're doing is we're transitioning the sample from a liquid or solid state into the gaseous state, which makes it easier to manipulate. We get the oxygen, which is dosed directly onto the sample from an oxygen cylinder that sits on the side of the auto sampler. The heat itself comes from a resistant furnace. So depending on the settings, the mode, the analyte you're looking to quantify, there can be different temperatures used. And of course, the fuel itself is the sample. If the sample is not very combustible, we can add combustion aids. We won't get too far into that today since we're typically working in the organic space. The first thing that we have to look at when we're talking about elemental analysis is our sample preparation. So of course, the sample, we need to get it ready for introduction into the combustion analyzer. And that's kind of our first step when we're looking at the overview. Once the sample is prepared and it's inserted into the instrumentation, we view the sample combustion, we change over into a gas before converting over into uniform compounds. What this does is helps us to manipulate the gases and separate them so that they can be analyzed and detected by the TCD, which is the typical detector we use in the instruments, which we'll touch on later in the presentation. So Elementar, as an organization, has a magnitude of instruments. Today, we'll focus on the Vario EL Cube, just as a showcase, for example's sake, to explain the general parts of an analyzer, kind of industry or manufacturer in specific. We'll go through all the parts that an analyzer would need, and then what Elementar does to support those needs. What I have here for you all is a video just showing the overall process of what an elemental analyzer does using that showcase instrument, the Vario EL Cube, in order to display the relationship. And so as we go through the video, I'll describe what's happening, and then in further slides, I'll break it down into steps. Samples being inserted into the combustion chamber, where it turns into a gas, and it goes through the combustion tube and reduction tube before it becomes separated. What you see now is the sample combustion gas moving through the absorption columns. And the absorption columns are what help us to separate the gas mixture into individual isolated compounds so that we can analyze those adequately by our detector. Down at the bottom, simultaneously, what you'll see is peaks forming, and that's because we have gases moving through the system hitting the detector. Once they hit the detector, an area count is formed and a peak shape or chromatogram can be identified in the software. The nitrogen is not trapped and moves straight over to the detector when we're looking at our elemental analyzers. And so the secondary peak that we'll see here is carbon. And so that last column actually catches the carbon as it moves through, allowing the remaining analyte gases to move over into the detector. That will happen once more with hydrogen and sulfur. At the end, sulfur being the highest temperature for release. Great. And what does this really look like? When we're talking about sample introduction, we need to somehow get the sample into the elemental analyzer, right? So there's a bunch of different ways that we can do this. And so when we're looking at solid samples, especially on the smaller scale, we typically use a sample carousel. In this graphic here, we can see the cover of the carousel, the sample carousel itself. And what this does is it will spin and rotate in a direction so that the samples that are placed inside the positions can move and fall with gravity, through the introduction point and into the combustion chamber. So I have just a quick video of here to display what that looks. So this is the auto sampler shifting. The samples that are in those positions you can imagine would be shifted over, dropping due to gravity into the system. Once it's entered into the system, where does it go? Something must purge this sample and ensure that we don't have any atmosphere being pulled in and being quantified with the sample itself. So what Elementar does to combat this is we have a ball valve complex. So this complex sits directly under the sample carousel and catches the sample once it drops due to gravity. It acts sort of like a cup, and so the sample falls directly in before turning 90 degrees. If you can see here my cursor, hopefully that's visible through scaring my screen, there are two gas entry or exit points that are connected to the ball valve complex itself. And the reason that we do this is because we're going to flush it with a carrier gas. In addition to the oxygen that was mentioned earlier, we do need a carrier gas in these instruments in order to push the sample gas through the instrument all the way to the detector in terms of the gas path, and then as well as to use it as a reference if you're using a non-specific detector, which we'll touch on later as well. So the sample cup is sitting upwards, our sample falls in, we turn 90 degrees where we flush with this carrier gas for blank-free sample introduction, finally turning 180 degrees for the sample to actually enter the combustion tube. What does the combustion tube look like? So in addition to the combustion tube, with CH&S analysis, we're also typically looking at a reduction tube in order to manipulate those compounds turn them over into uniform compounds in order to adequately separate them. When we're looking at pyrolysis and sometimes TOC analysis, we'll just have one reaction tube. And then sometimes when we're looking at larger sample sizes on a macro size analyzer, we may have a third tube to ensure complete conversion of our compounds. In addition to the reaction tubes themselves, we also have drying tubes to remove any water from the sample. Depending on if we are or we are not analyzing hydrogen, these may be introduced. The instruments with Elementar have a 3-stage drying system. So they actually have a condenser, a membrane dryer, and then this chemical drying, this desiccant that you see here. A lot of manufacturers are using Sikapent, which has since been discontinued. So Elementar's substitute for the desiccant is wet sorber or wet sorber S, depending on if we're analyzing for sulfur or not. The temperatures of these tubes, as I had indicated earlier, can change depending on the analysis. When we're looking at sulfur, we want to combust at a higher temperature than when we're not looking at sulfur. After we move to the reduction tube, what happens to the sample gas? So this is where we begin our advanced purge and trap for our gas separation. So the sample gas is heated after the reduction tube. All of the lines, we want to ensure there's no trace condensation of water, and that's also to ensure accurate hydrogen and sulfur concentrations. We don't want any sulfuric acid forming inside of the instrument either. So all the lines are heated after the reduction tube, and what happens is that the sample gas in its entirety and its mixture moves through this SO2 column. So this is what it looks like in real life. All of the connections inside of Elementar's instruments are ball and pan. Some other manufacturers may use screwdrivers and things like that, but regardless, there will need to be a way in order to access these absorption or separation columns. These columns themselves are circled right here in the graphic, so we can see a better look where they come in terms of the instrument pathway. Once the gas mixture enters the SO2 column, only the sulfur sticks on that, and the remaining sample gases move through. You can see the same for hydrogen. We analyze that as water and carbon as carbon dioxide. Again, nitrogen not being trapped, moving directly from that reduction tube over to the detector. The software then initiates a heat up function with the CO2 going first. You can see that column is the closest one to the detector. Makes sense. We'll heat it up, release the carbon gas, move through, heat up the hydrogen trap, release the gas, and then the last one will be sulfur at the highest temperature. So the software is actually smart enough and waits to the end integration point of each peak in order to ensure very good separation. And that's extremely important in high carbon nitrogen ratios, which we see a lot in agricultural samples. Great. So after we have separated out our gases, we're able to send them over to the detector. A standard detector, most elemental analyzers will be a thermal conductivity detector, which is a non-specific detector. And so I mentioned the use of a carrier gas. Typically, you'll see helium usually provides the best precision and accuracy at the lower end. It provides a greater thermal conductivity difference because as you can see here, what we're doing is we're comparing a reference cell to a measurement cell. So that reference cell will be explicitly carrier gas, and the measurement cell will be carrier gas plus the actual analyte gas. In addition to helium, we also have instruments that could use argon. We can switch back and forth between the two. Carrier gases, as we know, helium, was hard to source for a while and is still expensive. At least my price over with air gas has been here on Long Island. And so in addition to the other TOC instruments, which might use synthetic air, what we'll see most readily is a carrier gas moving through one side and the gas mixture moving through the other. Because the detector is non-specific, there's no differentiations of gas possible. So all the detector is able to see is that it's not carrier gas moving through. And this is what makes those absorption columns and this gas separation mechanism very crucial. Because if we don't have proper separation, what we'll see is peaks start to overlap and the detector become falsely inflated. And so that was Elementar's kind of advantage of introducing those advanced purge and trap columns, is really to improve that separation of the nitrogen, carbon, hydrogen, and sulfur peaks in a simultaneous analysis. How do we get from this peak area that's obtained to the actual analyte concentration? And so what we're doing here is we're taking a look at the chromatogram, just trying to extrapolate the idea of how we get from this to numerical values. And so what we see here is our N, C, H, and S peaks. And what happens is integration. So that happens automatically within the software. The software is able to dictate when the peak leaves the baseline, when it hits its maximum, and then when it returns to baseline. So at the start and at the end, there will be 2 pink integration marks. And so a theoretical line will be formed underneath, and the area under the curve is actually calculated. This area that's calculated is compared to that during the factory calibration or most recent calibration on the instrument in order to obtain the mass of the analyte. We then take the mass of the analyte and compare that to the sample weight, which is entered in the software. And that's how that we are able to come up with a percentage or a weight percent. In order to evaluate our result, we just want to make sure that the instrument is functioning well, both in terms of its overall hardware and service, but also for the application. And so what we'll typically do is we'll start today with running blanks just to purge the instrument, make sure that there's no residual analytes stuck in any of those columns or any atmosphere that may have entered the instrument. And then we'll follow by running conditioning samples. We here at Elementar call them run-in samples, but kind of to be in specific, conditioning also works here just to prep the analyzer to receive something other than a blank. After this, we'll run daily factor sample. So again, Elementar nomenclature, but looking more wide term, this is commonly known as a drift correction sample. This is what we recommend instead of coming in and recalibrating the instrument on a daily basis. Of course, that's an option, but what we do is we calibrate the instruments at the factory, long range, multi-point calibration, stable for years, especially for carbon and nitrogen. When we talk about sulfur, I'd say maybe 2 years as compared to the 5. After we run these drift correction samples, we want to make sure that our average and standard deviation between at least 3 of these replicates display good reproducibility and good precision. So we have internal specifications for that as well. If we're able to go through this startup routine, as well as check a matrix specific standard, we know that we're able to continue using the instrument for any unknowns with confidence. Alrighty, I can't see the chat I'm presenting. Well, hopefully we got some questions on the general parts of an analyzer, because now I'll transition more into the sample preparation side. So the most important part of sample preparation is going to be the balance work, so how the sample is weighed. And that's because as we just heard about a few moments ago, the percentage that is produced is based on the weight that's entered into the software. And this is why that balance work is crucial here, because any change, any alteration can greatly impact our accuracy and precision. As a rough guideline, we just want to make sure that we're using the proper sensitivity balance for the weight that we're looking to weigh. In addition to using the proper balance, we want to make sure that our sample is homogeneous. And I know this comes up a lot, especially in the agricultural space. I'll touch on a project that I was just recently working on with maybe a colleague, maybe someone you know in the industry as well, in order to help kind of assess this for soil carbon. But homogeneity itself is the degree of uniformity or composition throughout the entire sample matrix. So typically there is a relationship between homogeneity and sample amount, and we'll touch on that later as I had indicated. The larger the sample amount, the higher the homogenization. So if we have a very large sample, we're able to go without milling necessarily, or mill it to a larger particle size than we are. If we have a much smaller sample, we want to make sure that's much more representative. And that's kind of the benefit to using some of Elementar's larger size macro analyzers, is that we don't have to put in the work in terms of sample prep, which just makes the throughput a little bit easier and a little bit faster. Again, on the micro size, you'll see most of these analyzers maybe in universities, research facilities, does require typically a higher homogenation in order to get the same precision as you would using a larger sample size. Okay, to give you an idea of what prepping a solid sample looks like, I have a video here. So once again, I'll narrate it as we go through. This is one of my colleagues from headquarters. I do just want to mute it. Can you hear me? Great. Okay, so what you'll see on the right is a sampling container. This has all different sizes and materials of encapsulations. And so when we're looking to wrap the sample, we have options between silver or tin. Typically, tin is the material of choice because it does exhibit an exothermic reaction, boosting the local temperature up to 1800 degrees Celsius, helping with the burn and the combustion of the sample. Silver we'll use in pre-acidified samples because the tin, of course, would decompose. And if we have a sample that isn't burning very well, we can wrap it again in tin. So what you see here is she takes the empty tin, she puts it on the balance, tears the balance, adds the sample, and closes it up. So in terms of overall steps, it's very easy. What we can see here is a very, very small sample size being prepped for one of our microanalyzers. And so we see the use of forceps. In larger sample sizes, we can use even larger foils, and you can see them being added right here into larger boats or even cups if we're looking at a macro size analyzer. I did mention in the beginning that we also have the ability to analyze liquid samples in addition to solid samples. And so I just wanted to make sure that we displayed what that would look like as well. I know soil extracts come up a lot and things along that line. So let me mute this once more. What you can see here, she begins to tear the sample container just like we did with solids. But this time what's going to happen is instead of adding the solid material, with a spatula or a scoopula, as we used to like to call them, we'll use a pipette. So you can use a regular disposable dropper. That's absolutely fine too, because in the end, what we're using is the weight, just like we would with a solid sample. So this is kind of Elementar's or the industry's way of going about running liquid samples with a solid setup. After she enters the sample, which is a little bit easier with a micropipette since you can control it a little bit easier, she puts it in what we call the capsule sealing press. What this does is just makes a complete seal on that capsule as compared to squeezing it with the forceps in the previous video, just to ensure that there's no ambient air inside. There is also a flush option, if you can see right here on the side, if we wanted to connect a carrier gas to it in order to flush any ambient air out at the top. There's also an option to overfill capsules and kind of clean them up with a Kim wipe in order to prevent any headspace from forming in the top of the capsule. Okay. When we're looking at these very large sample sizes, Elementar decided that it was much easier to go about a reusable container solution than it was to load very, very large tin foils. And that's also because of the ash that's produced, right? The bigger the sample, the more tin that we need to wrap around it. And so the more ash that's produced from combustion. What we see here is an automatic sampler with reusable crucibles. So crucibles come in two materials. They come in steel, they come in ceramic. I'll have some further pictures of those in coming slides. But with our larger size analyzers, so the Vario Max Cube, the Rapid Max and Exceed, and the Solitalk Cube, which we'll touch on later in the slides as well, we use this automatic Vario Solid Sampler, we call it. So other manufacturers also have automatic samplers. Ours has 90 positions. These can hold up to 5 grams of sample and they are inserted vertically. Just like we have that ball valve complex on the smaller sample size, what happens here is as this gripper arm drops the sample into the combustion chamber, we're flushing with carrier gas just like we are in the ball valve complex. So in both instrument options and in both feeding mechanisms, we do have a blank-free sample introduction. Here it's great because like I was talking about before, making sure you're using the proper balance sensitivity. When we're weighing these larger samples in crucibles, a microbalance is not typically required for daily operation. This also means that we don't need to homogenize the sample as much as we did, excuse me, if it was on the smaller side. So that takes away the need for grinding or milling, at least to the same capacity that you would. High sample flexibility. So if the samples do have a high ash content, instead of falling into the ash crucible, which sits in the combustion tube in a microanalyzer, these larger size instruments are able to actually contain the ash inside the ash crucible, inside the sample crucible, which is then picked up and dropped off in a waste container. So not only is the sample prep side a little bit easier, but also you don't have to go in and remove the actual ash. It's actually automatically moved over to a waste container for collection. Using crucibles is very similar to the way that we weigh our samples in tin. So we'll place the crucible directly on the balance, we'll tear it, and we'll add the sample. Here it's a little bit easier because we don't need to encapsulate it. So maybe a little bit quicker for high throughput laboratories who are measuring a lot of samples. If you're measuring trace level elemental concentrations, we'll typically recommend baking out crucibles just to make sure that they're absolutely clean before analysis. But in terms of cleaning them after analysis, there's not much that needs to be done at all. And that's because all of the organic material is being burned off during that combustion, right? And so what we can do at the end is just give it a gentle knock on a lab bench. Some people, if it's really difficult to remove, if you've used it time and time again without knocking that ash out, just use maybe a screwdriver to remove or loosen up the ash. If you're working with a very salty application, salty samples, the crucibles themselves, these photographed here at least, are made of steel. And since salt is water soluble, we can just toss them in a water bath without any concerns. This goes for both the crucibles and the tinfoil sample preparation options. That solid material should be thoroughly mixed before sampling. Again, going back to that homogeneity, making sure we have a very representative sample. Of course, this will help with accuracy, but it's even more kind of important for precision to make sure that each sample is equally represented. For liquid samples, depending on what part of the liquid we're trying to analyze, if it's a supernatant or not, obviously we're not going to go in and stir it again and try to take a representative sample of everything. But if we're looking to sample something with particles, we want to make sure that those particles are well suspended before we stick in our micropipette. When we are using crucibles, even if we're using foils, we do want to avoid touching that with our hands. Obviously, we do have oils on our fingers here. And of course, if you're handling any hazardous samples, you want to touch those as well. If the samples need to be dried, we do have, general procedures that we could recommend, but it usually depends on the application and any standard compliance that you're looking to kind of meet with operation of the instrument. Righty. So we talked a little bit about what an analyzer looks like, what the parts are. We talked a little bit about what needs to be done before the sample is analyzed in terms of sample preparation. And now we'll talk about how to take care of the instrument. What does it look like to own or operate an elemental analyzer? So at least with Elementar, what we have is an automated maintenance counter. So in some way, shape, or form, regardless of manufacturer, you will need a way to keep track of how many samples are moving through this combustion tube, this reduction tube, this drying tube that we touched on. And then kind of on the hardware side, we also want to look at maybe how many samples are going through the ball valve complex. After a while, we'll give it a clean, and so on and so forth. So what this automatic counter does is it uses an interval. It's a preset default suggestion that's input there for typical samples. So the way that these were created were usually by running pure chemical standards. So they will need to be adjusted according to your own experiences. So your own sample weight, your own sample type, and things along that nature. After a certain number go into the standing interval, I believe it's 75% of it, the actual maintenance action will change color. So it'll change from green to orange and then eventually red. If you go over 100%, it'll actually blink at you. And you can even set it up so, so a lot of universities will have it such that you can't perform an analysis before the maintenance action is performed. What does maintenance look like? So one of the things that we'll have to do eventually is change out the tube. So sometimes the tube material itself can be reused, but the chemicals inside of them do need to be refreshed. And so this is what it kind of looks like to exchange the reaction tubes, and in this case, demonstrated for our unit cube. Very similar to the Vario EL cube, both CH&S analyzers. So the first thing we want to do, she's going inside of the software and she's actually going into the replace parts function. What this does is it cuts off the carrier gas so that we can manipulate the connections inside. Again, regardless of manufacturer, you will need a way to shut off the gas so that you can take out the furnace, take out the tubes. All of the doors are magnet on Elementar's instruments here. And so in addition, what you'll see is all of our connections are ball and pan. So you don't need any tools. I think I might have mentioned that earlier. And then she's also releasing a bayonet clamp. That bayonet clamp just keeps the combustion tube connected to the ball valve. She's now removing a heat shield. What this does is ensures that the sample gas stays hot after reduction. I had mentioned that earlier as well, just to ensure accurate hydrogen and sulfur concentrations. Once those three parts are removed, she's able to completely roll out the furnace. This makes it a little bit easier to manipulate the tubes. She's now disconnecting what keeps them together, the combustion and reduction tube, which we call the quartz bridge. And just like any other connection, you'll see two black seals or O-rings there. My colleague is removing the tube when it is completely up to temperature. So this can be done hot, this can be done cold, it can be done anywhere in between. We always recommend doing it hot if possible. Of course, that reduces any downtime, but also reduces the chance of bulging and changing the shape of the tubes in the furnace itself. Kind of ensures a little bit longer of a lifetime. But if the analyst isn't comfortable with it, or if you have some extra time and maybe not super high throughput of samples, you're more than welcome to let the furnace cool down and then make the swap. Tubes, I did mention can be reused. So typically we're talking about steel tubes in that case. Our analyzers that not looking at sulfur, we can use steel here because steel will adhere to our sulfur, of course. So for our nitrogen protein analyzers, for our carbon nitrogen analyzers, sometimes you'll see steel tubes. These are more readily reused, they're a little bit more robust. And what we can do to make sure that they're not bulging when we take them out of the furnace, especially if we've used it around 2-3 times already, is just give it a little roll on the lab bench, right? Make sure that we don't get any wobbles, which would indicate that the bulging has already started and maybe we wouldn't want to put this tube directly into the furnace, right? We don't want it to get stuck. We don't want it to alter shapes completely and damage any part of the instrument. What you'll see here in the photograph is quartz tube. So when we are analyzing for sulfur, we do use quartz. And in this case, the tubes themselves cannot be reused, up to 5 times. But we do want to make sure that we're looking out for any devitrification or recrystallization of that quartz if we were to reuse the tubes. I mentioned the removal of ash. This is another maintenance event. In addition to exchanging the tubes inside, is actually just emptying or exchanging this ash finger. So we can see the tube packing a little bit more blown up here inside of our quartz tube. We have a protective tube on top, our actual ash finger. So this is where our oxygen is dosed directly through an oxygen lance, completely customizable in the software if you want to increase, decrease O2 dosing parameters to save a little bit on cost, to save a little bit on maintenance efforts, then we can absolutely do so. So sample comes in here, dosing happens right during the ash finger, and this is where the ash will remain after analysis. This is followed by our combustion aid or our catalyst, which is tungsten trioxide, quartz wheel, and a support tube to hold it in place and push it up into the hottest part of the furnace. Again, if we were to remove this, what we'd want to do is go into that software, select the replace parts function to cut off the gas. You don't actually need to remove the tube itself. You can do it when, again, the furnace is hot, the furnace is cold. You can leave the furnace inside and use tongs to just remove or exchange the ash finger. As I had mentioned, that is not needed at all when we're looking at the automatic crucible technology. And what we're able to do instead is just move this sample over to a waste container. So this just shows a little video again. Apologize for the sound here. My Zoom options are in front of me. But this is our gripper arm picking up the sample and moving it over into the combustion chamber. And at the end, it'll take it out of the combustion chamber and move it over to the waste container. And so just like our oxygen lance, right, that ceramic tube, I said that's dosing oxygen in the combustion chamber. For our microanalyzers on our macroanalyzer side, the actual gripper arm has a hole in it where we can change the dosing of either carrier gas or oxygen. Okay. So hopefully that gives a little bit of an insight into elemental analysis, what it is, what it looks like, before we touch on some forestry context here for the last 15 to 20 minutes. So why does elemental analysis matter in terms of your industry? So we know the elements of life: carbon, the building block for all organic molecules; nitrogen, necessary for protein, same with sulfur, and then phosphorus and nitrogen for DNA as well. When we're looking at energy, we have the energy capacity even equation, which actually uses the elemental composition of the analytes, which you can gain from an elemental analyzer, in order to find the energy capacity of a fuel. Again, it contributes to pollution. So smog and acid rain, we're looking at nitrogen, we're looking at sulfur. Soil, huge, very important here. I know I touched on the high C to N ratios that we'll see in a lot of these samples. We want to make sure that we get that really good carbon and nitrogen peak separation to ensure that we're getting correct quantification of both individual analytes. In plants, can either be an energy or nutrition source. For energy, we're looking at carbon, hydrogen, nitrogen, and sulfur. So maybe that vario-EL cube, that unicube, that gives us a full 4 analytes that would be of interest to us. We have a larger instrument too called the vario macro cube, which can do a little bit larger of sample sizes for CHN and sulfur S analysis. For nutrition, nitrogen is important. It's characterized by total nitrogen content and then total dietary fiber. So we do have a total dietary fiber module that goes on one of our instruments if that's of interest to you. Please feel free to ask questions at the end as well. In fertilizer, we have some relevant standards, but we're typically looking at carbon, nitrogen, sulfur. Hydrogen's not super huge in fertilizer, but sometimes we'll get a request for that as well. I believe there is an AOAC standard for sulfur in fertilizer in progress. I haven't got a status update on that, so I'd be curious if anyone here knows a little bit about the development of that. Not that I expect it, but it would be pretty cool. This is some example data of what we're looking at. So these samples were obtained from a pasture in the southwestern United States, a little bit closer to home here for Elementar Americas. What we can see is expected concentrations of different layers of this soil horizon. Using the same instrument, our Vario Max cubes, that's one of the ones that uses the crucible and the auto sampler. We sampled another subset of soil from a banana plantation in Ecuador, using a slightly higher sample size here, typically because our analytes are a little bit lower. We can see here the next column for the carbon-nitrogen ratio, just to exemplify how high and how often we see samples of this nature. This instrument, again, was the Vario Max cube, but this time was utilized with the carrier gas of argon. So I know I hadn't touched on before the fact that helium became hard to source and became a little bit more expensive. And so a lot of customers transitioned over to argon, which on the bottom end of nitrogen doesn't give as perfect, right, of a sensitivity as helium does. But as you can see here, for these very low nitrogen concentrations, we were able to get great data using heterogeneous soils. Same thing here with helium. This is in fertilizer. Again, some example data. Feel free to request more of it later or to take a look at it when we have some extra time. Plant material also comes up a lot as well, especially with the high carbon concentrations that we have here. We want to make sure that we're getting a complete combustion of our sample. And this comes into play when we're looking at very low sulfur concentrations. We want to make sure that we have a large enough sample size to get a good area formed by, or good signal formed by our sulfur, but at the same time, we want to make sure that we're getting complete combustion and not overloading the sample size due to the nature of carbon. In biomass and biochar have come to our attention in the coming years. I'm hoping that some of you are working in that field as well. I'll be happy to talk to you about it. A lot of the CHNS data has now kind of transitioned into a heavy focus on TOC data, but regardless, we run the samples on both instruments. I'm happy to talk about both. And last up, just nitrogen and animal feed. This will come up. Nitrogen protein. We do have instruments that are explicitly geared towards analyzing nitrogen. This diagram here just gives us an extrapolation between the difference of using helium and argon for different feed samples. Okay. Just to touch on TOC before we end up here, I know this is big and we didn't get to talk too much about it as a more introductory to EA and elemental analysis and soil agricultural applications, but it is a big topic and I will be talking about it coming up at ISSPA. I think some of you will be there. I think Alta is sponsoring the event. I'll show a slide on that at the end as well. But organic carbon, main source of energy for microorganisms, is bioavailable. Elemental carbon, which doesn't have a perfect definition, but we do know that it's inert and it's not bioavailable. And then again, slightly better definition once again of what defines inorganic carbon, also inert and not bioavailable. Why does it matter and how do we define it? We have 3 general methods that can be used depending on how your analytical capabilities, right, what instrumentation you have, and then depending on the sample type itself. So method 1, the most common method, is the determination of organic carbon at combustion temperatures over 900 degrees, so typical total carbon, but with prior acidification. Method 2 is the determination of TOC at lower combustion temperatures. And method 3, that we'll touch on, is the determination of different forms of carbon using temperature ramping, more on the innovation side, the newer method. So it looks like a lot of text, I know. What this is just showing is which instruments comply with which methods and which ones can be used for different sample types, and kind of what the data would look like extrapolating from those differences in analysis capabilities. What are the concerns for TOC determination via acidification? So we've been doing this way for a long time. Why change it? Very good question. We have minerals like calcite, magnesite, dolomite that are either very easy to decompose or very difficult to decompose. And so when we're adding acid, we have to make sure that we're adding enough acid, that we're adding the correct acid. Not only does this take up a lot of time, it's a little bit hazardous, and it's also produces a slightly more wear and tear on the elemental analyzer, of course, when we're operating with steel, right, as well. And so Elementar solution for this was the Solitalk cube. And this is our instrument that can ramp temperatures. We go from 400 to 600 to 900 degrees in order to quantify that organic carbon, that elemental carbon, and that inorganic carbon. This is all in the presence of oxygen gas as a carrier. There's a secondary method where we do switch in the middle, and we go from oxygen to nitrogen back to oxygen. We call that the gas switching method, with the middle stage being pyrolysis. And that does help to separate the TOC peak from the ROC, that elemental carbon, residual oxidizable carbon peak there in the middle. At all parts of this analysis with the Solitalk cube, we're analyzing carbon dioxide. So we're ramping temperatures and we're watching this carbon's combustion profile come through. So when we look at this, if we're used to traditional elemental analysis, we're confused by the separation of these peaks. They're not the typical shape that we're used to observing here with our absorption columns, giving us that good separation and that clean peak maximum. And the reason for that is because when we have especially agricultural samples or environmental samples, we have different carbonates that are being released at different temperatures. And so what we see here is the first peak is at 400 degrees, the second is after 600 degrees, and the last one for inorganic carbon is at 900 degrees. And so these temperatures were selected based on the DIN 1935 method, but they can be adjusted inside the software in the case that you had a research focus and wanted to manipulate the temperatures and able to review the release temperatures of the carbonates that you're looking at. As an overview here, we drop the sample in with our gripper arm. We're dosing either with nitrogen, with oxygen gas, depending on the mode that we're moving into. Very simple, like I said, with the TOC, just one reaction tube itself. We have a drying tube, also a halogen tube. If you have any halogens in your samples, that can be filled with brass wool, silver wool, whatever you can get your hands on there. Silver wool is typically a little bit better, a little bit more expensive. So we'll see brass wool for the most part. After that, you'll see the carbon peak come through, the first one being the peak from the 400, second from 600, last from 900, depending on the temperatures that you set and the heat rate that you set for the instrument. The reason that I bring up this instrument is because I did partner with Bob, who I believe is in attendance today. We discussed working on this project where we would assess soil carbon measurement precision, comparing the fineness of grime between different amounts of total carbon in samples in an effort to provide a 3D surface response. So basically, what size sample and what degree of homogenation will we need to achieve a certain precision? And so in order to test this, we used our Solitalk cube, the temperature ramping instrument that I had just touched on a moment ago. Skip you with the 300 sample master data sheet. Don't want to bore you all with that, but kind of the end result here, which is color coded to help review the effect. So what we see on the left side is the sieve or the grind size, and on the top is the sample weight that was utilized. So from left to right, on the top, we're going from smallest sample to biggest sample. From sieve side on the bottom, we're going from smallest sieve side to largest. And what we can very visually indicate is this trend heading from a large sample with perfect homogenation at 0.1 millimeter sieve size is going to provide the best precision. And of course, we knew that. But now moving forward, what we're able to do is kind of extrapolate what exact sample size and what exact sieve size will we need in order to achieve our desired precision. That's replicated down in the bottom for 2 different samples. This is just a photo of real life that I took when I was over in the application lab over in Germany that I was talking about, where we are headquartered. And this is kind of what the auto sampler looks like when it's filled up with those reusable sample crucibles. So I had sat there at the balance, prepared these, brought them over on a sample tray, and using tongs, I just loaded them into the auto sampler. And I'm looking forward to talking a little bit more about ISSPA. Bob will be doing a poster on it, so I don't want to give away too much. I know that Shiny will also be there. She was our Elementar contact who connected me with Bob and kind of formed this relationship. So thank you for that, Shiny. Thank you, Bob, as well, for the samples and for the opportunity. I'll be doing a presentation at ISSPA for whoever will be there. For whoever who won't, it is the International Symposium on Soil and Plant Analysis. Speaking with Corey before we hopped on, I believe he mentioned that we're sponsoring, or Alta is sponsoring the event. And so I'm assuming that a lot of people will be there. So excited to meet you all in person and talk a little bit more about soil. If you'd like to connect with us in the meantime, I've just thrown some emails on here, as well as the Elementar Americas LinkedIn page. So please connect with us. I'd love to chat a little bit more at any upcoming events or even online remotely like we are here today. All right, and that's a wrap. Thank you, Corey. I apologize if I went a few minutes over there.
No, that was perfect. And I got to say, I really enjoyed the webinar. So real fast, I just wanted to share screen. I know we have some CCAs on. If you want to get your CEUs for today's presentation, you can use the QR code below and scan it. I know sometimes we have some issues with the QR code in the phone app. So as always, just shoot me an email and I'll make sure you get those CEUs for today's presentation. And with that, I do want to transition to Q&A. I have some questions lined up, and while I may kick it off with some of my questions, but everyone else, please feel free if you have questions to put them in the chat. And so with that, I will just want to make it so I can see the screen a little bit. With that, Jessica, I think one of the first questions that kind of came to my mind is, you addressed this at the end of it actually came later in the presentation, and you addressed this, but one of the biggest challenges some of our labs have that I get told about is the treatment of these acidified samples and the, I guess, challenge associated with that in terms of maintenance. And you hinted that there's increased maintenance when we acidify our soil samples. Could you just comment a little bit more on that? What does Elementar see? What are some things that people can be doing to just be prepared for that?
Yeah, absolutely. So of course, when we are looking at acidified samples versus neutral samples, we are expecting a slightly larger amount of wear and tear, especially on steel components inside of the analyzer. And so, of course, in the case that neutralization is not possible, we have to look kind of outwards as to what other solutions can we provide to reduce that wear and tear on the instrumentation itself. First and foremost, we did very basically touch on it, but the use of silver foils is very important, not only because the tin will decompose, but it does keep the sample fully enclosed and prevents it from damaging the inner tubing. Again, we can always wrap that with tin if we need to. And then on the other end, when we're looking at instrumentation that doesn't require acid in order to determine these carbon fractions, we kind of take away that concern completely.
Another big topic that you hinted at already is this cost of the helium challenge in labs, and the switch to argon. And I know you mentioned specifically that there's some loss in sensitivity on nitrogen on the lower range. Can you just comment a little bit more on so I know that, I'm not sure specifically with Elementar instruments, but maybe broadly with combustion instruments, there's a change in maintenance requirements with our maintenance usage and the speed at which consumables get used and things like that. What are some broad challenges that labs face when they're making that argon shift? Can you comment a little bit more on that?
Yeah, absolutely. So depending on if you're using a micro or macro analyzer, you might have an easier transition. So when we're looking at a larger sample size, we're able to produce a larger signal area to the detector, which is kind of the culprit. So when we're working with a thermal conductivity detector, we're using that carrier gas as the reference side of the cell. And so what we're doing is we're extrapolating the difference between that reference gas, thermal conductivity, and the sample gas thermal conductivity. And so explicitly when we're talking about nitrogen and we're comparing the thermal conductivity of nitrogen to helium versus the thermal conductivity of nitrogen to argon, we have a bigger difference with helium. And this bigger difference allows the detector to see helium, as you could say, on a lower concentration level, which enables that better precision on the lower end. Now, when we're working with argon, we're transitioning over. If we're able to increase the sample size in order to increase the signal, then we can kind of circumnavigate any issues with the loss of sensitivity. When we're transitioning to argon overall, the main difference there, besides the signal that's actually produced, will be the heaviness versus lightness of helium and argon. So some of our customers will add little cover foil. Some of them we do recommend the use of an argon disc. It's a little apparatus that we put on side of the gripper arm, and that's just to ensure that there's no sample loss during introduction from the change in weight of the carrier gas that's used. So there are a few minor solutions that you can implement when switching over to argon to kind of give yourself more confidence if you're used to using helium in the past.
Yeah, I appreciate that answer. And so I do see a couple chats questions and we're going to
Sure.
get to that in a second. Bob, I see you just went off video, or I mean turned on your video. Um, so Bob Miller is our resident Alta advisor, science advisor. And so I asked him to come on and maybe both of you could kind of share a little bit more. So this question of sample prep is just a massive question in the soil carbon testing industry because the need to grind is key for accuracy, but it is also probably the biggest cost associated, or one of the biggest costs associated with soil carbon analysis. And so there's a lot of labs trying to figure out solutions like do can I do 2 milliliter or 2 millimeter grind? How fine do I really have to grind this? What is the right sample size? We saw some examples where you're using micro balances. Probably no one's doing a micro balance on carbon, but maybe more into like half gram to whole gram sample size. So I would just love if Jessica, if you wanted to kind of kick that off with just kind of some deeper thoughts on that sample prep challenge, some real clear like what is Elementar recommend people grind to and sample size when doing soil carbon analysis on soil, and then Bob, maybe you could follow up on that if that works for both of you.
Yeah, definitely works for me, Corey. Thank you. So, yeah, this project collaborated between Shiny with Elementar and Bob Miller was to evaluate and try to get an answer to your question, basically, is kind of what is the general requirement or suggestion that we would make to labs. And so, of course, like we displayed in that relationship across the organic carbon and total carbon results for the soils, was that the sample size also has a lot to do with it. So if you are working with a micro size analyzer, which we do see, typically universities, but they will be working with a smaller size analyzer for agricultural samples and carbon. And that's where we're kind of at a standstill sometimes because we know universities are not always the most affluent with their time and their costs as to sample prep. But at the same time, when we're looking at a smaller sample size, we really do need to ensure that we are properly homogenated in order to get precision within the wheelhouse that we expect. So internally here at Elementar, when we're analyzing, pure chemical reference standards that have a known concentration as well as a known combustibility, we always say under 0.1 absolute standard deviation is our basic requirement, just to ensure proper instrument operation and to be able to extrapolate replicates from one another. And so I'd be curious to hear if Bob has a recommendation because just looking at the charts here, I would say most of them are under that 0.1 absolute mark, which would mean looks like anywhere from 0.5 millimeters and below for any sample size was able to provide that precision, which meets our internal specifications. But looking more into the industry and what you guys have to meet in terms of compliance and comparing data between manufacturers, I'd be curious if Bob had a recommendation for a specific weight or a specific sieve size, or maybe he even wants to save that for his poster.
Thanks, Jessica. I'm happy to share it because I still haven't made the poster yet. So here's the deal. So when we get into this carbon analysis, it all comes down to what's our measurement uncertainty. And that was the whole objective when I approached Elementar last summer about this project about grind size and sample size, because I really wanted to know what's the optimum between the two. How big can we go, or how fine can we go in the soils, but how big a sample can we push through the instrument? And so we did two soils. One's kind of a moderately high carbon sample. I think it's 2.5%. The other one was a 1%. And that's the one that was probably going to challenge us because, you know, we're getting down into the lower detection range. And so we ground these soils to, as she mentioned earlier, they were 2 millimeter minus, 1 millimeter minus, 0.5, 0.25, and 0.1 millimeter minus. And we used, hey guys, we went back to old school. We used a granite rolling pin on a granite table, and we just kept sieving until we met that each one of those parameters. The end result behind the whole thing was, if you look at this surface response that we have on these two soils, it says that if we mill our samples to a 0.5 millimeter minus, and that's 100% of the soil sample passing that, and we use a 500 milligram sample size, we can achieve RSDs of less than 1% based on 3 replications. Now, why is this important? Corey elaborates the fact that all of our soil testing business is done on a 2 millimeter minus using a flail mill. And the problems with the flail mill is it just beats these soil aggregates down until they flow through the screen. And I can tell you, I've been in many labs that do this on an automated basis, so to speak, and they may discard 10% of the sample that just doesn't go through the screen. You know, it's either very coarse sand or it's approaching gravel or aggregates that just don't pulverize within a 30-second time frame. When we look at this carbon analysis across the world, most of our competitor labs in the other parts of the world are using ring mills or some kind of ball mill to pulverize the sample. And the problem with that is this just rapidly increases the sample prep cost. The instrument cost is the instrument cost, but the sample prep cost becomes very high. And my whole objective of this study was, well, what can we get by with? And obviously we could run 1 gram sample sizes through the instruments and 1 millimeter minus, but that's just not realistic in terms of the usage of the consumable supplies in the instrument and, you know, the amount of work. And I got to tell you, I was worried that we were going to have to grind our samples down to 0.25 millimeter minus, which again is added sample cost. But it does appear, looking at this data set of these two soils, that the sweet spot's 0.5 millimeters and 500 milligrams, which is really, you know, a very achievable thing to do. So, yeah, very interesting. And by the way, for those of you coming to North Carolina in June, we're going to have inorganic carbon, ROC, and total carbon on these samples. So you'll be able to see all this analysis side by side. So it's been a great project. Got another one in the planning. We got to figure out what's the best way to grind these samples. And I got to tell you, I don't think flail mills are our best answer. There are some hammer mills out there that might make this an easier thing to swallow in terms of sample prep. The other thing is there's several labs in the US that use a Beco plate grinder. Very slow, but you don't have to handle the extra samples. So any questions?
Yeah, so Bob, I love that, and I'm glad that you two are the people saying you need to grind to 0.5 millimeter, because I know that's not a popular statement with some labs. But I think we need the data to say this is necessary so that we can justify the cost as a lab when we go and talk to the people paying for this carbon analysis, because it really gets to the real issue with labs, which is that there's like there's a stool set up, right? You can either have low cost or low cost, you can have fast, or you can have quality, but you can't have all three. You get two. And
Yep.
so that's this triangle is just damaging in a lot of spaces. And so being able to explain, look, this is a costly analysis, and if you want quality, which I think a lot of people looking for carbon markets want quality, then it just costs that this is what it costs, and this is how to do it right. Jessica, we have some really, oh, sorry, Bob, go ahead real fast.
I was just going to say, I'm now averaging 2 questions a week about this very subject from the client side. And in fact, I was just doing an email this morning with a colleague back in Nebraska about this. I'll got to say this. If you do the back of the napkin calculations on measurement uncertainty based on RSDs of 5 or 6%, this carbon market will dry up like a drought. I mean, it will disappear. But if we can get this precision down in the lab side, down under 3%, I think we can find quantifiable information that has dollar value. And I'll leave it at that.
I agree. Jessica, we have some really specific questions in the chat. I think about some of your instruments. The first question would like to ask why the SciCapNet. I'm not sure if I'm saying that right. Can you see
Oh,
the
I see it here. Yes,
Yeah,
yes. Why was
was
Sycophant
yeah.
discontinued?
Yeah, can you comment
I'm
on
not
that?
100. Yeah, sure. I can definitely comment on it. Unfortunately, I don't have the end-all be-all answer. As far as I know, Sycophant was produced by Merck. And Merck is a separate chemical manufacturing company from Elementar, from any other analyzer manufacturer. And so we weren't actually producing it in-house. It was a third-party desiccant that we were obtaining from a separate company, and that company decided to discontinue the Sycophant. And then, response to that, Elementar created their own desiccant, which is wet sorber or wet sorber S for sulfur analysis, and that's to supplement or to replace Sycophant. And so direct replacement, super easy to use. If you have any questions about that, I might be more equipped to answer them than unfortunately discontinuation of Sycophant.
No, and I think that was multiple instrument companies have moved to their own kind of in-house desiccant. So that's a good question, though. The other question, why is the leak test performed with empty dry tubes?
So when we transitioned over to the wet sorber or the wet sorber S, one of the benefits of it is that it's a free-flowing granulate. And so when we were working with Sycophant, it was a sticky white powder that turned blue when it was used. So we do have a color indicator in ours. But basically the difference between loading that full tube with powder and loading it with granules does have a change in the flow. So how much carrier gas is moving through that tube and at which speed. And then so we didn't actually go in and perform any remote updates of the softwares when we pushed out and started offering this chemical. So just to keep things easier and to keep the cost lower for the customer, we suggested that for certain instruments specifically, I know the Rapid and Exceed is one of them. I think the Vario Macro Cube may be another, just easier to remove the tubes and to go through any update to the leak test, which would have to change the expected flow.
So I know we're at the top of the hour, and I do want to wrap kind of close to on time here, but I did have one question I thought was really good that I get a lot when I talk to instrument technicians that maybe aren't super sciencey about about what's going on, but just they run the instrument and they're core and necessary for getting the work done. And that's kind of in this space of that sometimes you put samples on this, you load them and they just sit there on the auto sampler. And so does moisture changes as they take in moisture from the atmosphere? Does that change as they just sit there in the crucible? How does that impact things? What are your concerns there? I know sometimes there's also this question of like, am I trapping some of the nitrogen that's in the air as part of the sample? Can you just kind of speak broadly to that question?
Absolutely. Yeah. So when we're looking at those micro size analyzers and we're prepping our samples in foils or some other type of encapsulation material, what we'll usually do, especially when we're not working on such a small sample scale or sample size, is we'll put them through a manual pressing tool. So basically it's a hand plunger. And what that does is it uses force to expel any of the trapped air inside of the sample, which could lead to inflation of nitrogen results, so on and so forth. So for solid samples, we'll put it through that plunger to expel any ambient air from being trapped. Now, when we look at the open crucibles, this is a question that I'll get a lot, because when we load the samples up on top of that 90 position auto sampler, especially for high throughput customers or laboratories, they have them sitting up there waiting for the next sample to be analyzed, waiting for that complete 90 before they restack and reset with new samples. And so the Vario Max Cube, the Rapid Max, and Exceed, and the Solid Talk are the three instruments I mentioned that utilize this crucible technology. And so none of those instruments actually analyze for hydrogen. So the moisture can change when the sample is sitting on top of the auto sampler, but it does not have any impact on our results whatsoever. And that's because we go back to the importance of sample prep and weighing. So when we take the weight of the sample, so long as the sample is dry at that point, what we're going to do is load the sample on top of the auto sampler. It'll sit up there for XYZ amount of minutes until the next sample, or until the user actually presses go. And then all of the hydrogen will be converted over to water and removed in that 3-stage drying system, including the sycophant replacement or wet sorber. And so since the hydrogen is not being analyzed, it's removed, and the nitrogen is being calculated based on that dry weight, like we said from the start. So as long as the samples weigh dry, your results will be on a dry basis. No concern for leaving samples up there for however long.
And I know in most instruments, if you don't want to assume your sample is perfectly dry, you can do a moisture analysis and do a moisture correction within the software.
Absolutely.
Okay, so we are out of time. I really appreciate the discussion this morning, Jessica. Thank you so much. And so just for a reminder for everyone, this meeting or this webinar has been recorded, and we will share it back out through our channels probably within a few days. So again, thank you so much. And with that, I'm going to go ahead and stop recording.